when you picture massive industrial infrastructure like a sprawling refinery complex or thousands of miles of high-pressure pipeline just crossing a freezing tundra, you naturally focus on the big, visible things.
Right, the obvious stuff.
Exactly. You see the foot-thick steel walls, right? You see the massive concrete foundations. You look at the sheer, overwhelming scale of the machinery, and you just assume the hero of that environment has to be something really heavy and structural.
Yeah, we constantly fixate on the armor. I mean, we look at the giant metal turbines and the heavy bolts, and we just assume that sheer physical mass is what's keeping all those highly pressurized, volatile chemicals safely contained.
But then you zoom in.
Yeah.
You look past the steel walls.
Yeah.
And you look really closely at the joints and the massive internal valves, and suddenly you realize that the difference between a facility running smoothly and a catastrophic failure isn't always the foot-thick steel.
Not at all. Sometimes the only thing holding back a total blowout is just a couple of ounces of a gray to black semi-plastic paste just sitting quietly in a microscopic gap.
It really is the ultimate unseen hero. I mean, it's a hidden barricade that takes the brunt of unimaginable pressures, extreme temperatures, and just a constant barrage of corrosive chemicals.
Right. Welcome to the deep dive. We usually explore broad concepts here, but today our mission is zooming all the way in on a single fascinating blueprint of extreme survival chemistry. We are unpacking a highly technical data sheet from a company called Jet-Lube, specifically for a product known as EZY-TURN No. 4 gate valve sealant.
Quite a mouthful.
It is, and I know dedicating our time to industrial valve goop might sound a bit dry on the surface, but as we get into the mechanics of how this substance works, it reveals an incredible story of engineering. Okay, let's unpack this. Why does your modern world rely so heavily on something you will literally never actually see?
Well, to understand the stakes, you have to think about what is actually flowing through those massive pipelines,
Right. We are talking about volatile gases, crude oil, and hazardous chemicals moving safely from point A to point B under intense pressure. And EZY-TURN No. 4 is essentially a highly specialized barricade.
How so?
Well, when a massive industrial gate valve closes to stop the flow of a volatile gas, the heavy metal surfaces of that valve, they don't perfectly seal on their own.
Even if they're machined perfectly flat.
Exactly. Even the smoothest machined steel has microscopic valleys and ridges. So without a sealant to fill those microscopic gaps, high-pressure gas would just hiss right through.
But we aren't talking about the kind of, silicone caulk you use around a bathtub, right? I mean, you can't just squeeze standard grease into an industrial pipeline.
Oh, far from it. No, this is a highly engineered semi-plastic compound that has to survive in environments that would instantly turn standard materials to ash.
Wow.
Or, freeze them into shattered glass. It serves as the thin gray line preventing leaks, stopping mechanical lockups, and just generally keeping hazardous materials inside the pipe where they belong.
So to really appreciate the armor, we have to look at the battlefield. Let's talk about the sheer physical extremes this stuff is designed to handle, because I was looking at the service ratings in the source document, and the numbers are just staggering.
They really are.
The manufacturer states it operates in temperatures from negative 40 degrees Fahrenheit, which, fun fact, happens to also be negative 40 degrees Celsius, all the way up to over 400 degrees Fahrenheit, or 204 Celsius. I mean, it's like asking a single material to survive being trapped in an Antarctic blizzard and a commercial pizza oven on the exact same day while still actively doing its job.
That's a great way to put it. And surviving the cold end of that spectrum introduces a major mechanical challenge. I mean, at negative 40 degrees, almost any fluid or grease will just seize up completely.
Right, it just turns solid.
Yeah. And the datasheet points out a very specific caveat for that low-end metric. It states that the sealant is still pumpable at negative 40, meaning it hasn't turned into a literal solid curl rice.
But I'm guessing it's not exactly easy to work with?
No, not at all. You can't just squeeze it out of a tube. To actually force it into the microscopic gaps of a valve at those extreme freezing temperatures, engineers have to use a specialized high-pressure lubricator.
That makes perfect mechanical sense. You have this semi-plastic paste that is desperately trying to solidify in the freezing cold, so you need immense mechanical force to inject it.
Right.
But it has to stay pliable enough to move into the gaps while remaining solid enough to block the high-pressure gas.
Exactly. It's a really delicate balance, but the heat resistance is where the chemistry gets truly bizarre. What's fascinating here is how the presence or absence of a single environmental element drastically changes the physical limits of the compound.
Oh, right, the oxygen thing.
Yeah. The data sheet has this incredible conditional metric. It states that the sealant can actually retain its consistency at an even more extreme 500 degrees Fahrenheit, that's 260 degrees Celsius, but only under one very strict condition.
Yeah, the document explicitly notes it can survive 500 degrees within a valve where oxygen contact is excluded. And this part completely threw me. Like, how does removing air from the equation suddenly make a material heat-proof?
Well, think about what oxygen actually does at a chemical level. At 500 degrees, you are pushing the absolute limits of the molecular bonds holding the sealant together. If oxygen is present at those extreme temperatures, it acts as a chemical catalyst.
Okay.
It basically behaves like a fire feeding on the carbon chains of the sealant. The oxygen triggers a rapid oxidation process, literally tearing the molecules apart, and the material just cooks and degrades.
It essentially burns up.
Exactly, it burns up. But if you starve it of oxygen, which naturally happens deep inside a fully sealed, liquid pressurized valve, that chemical trigger is just gone.
Wow.
The combustion mechanism is completely removed from the environment, so the compound simply holds together. It defies its normal thermal limits by basically holding its breath.
That is wild. Knowing what it can survive, the natural next question is, how? What is this stuff actually made of to possess a chemical profile like that?
Right, the secret recipe.
Yeah. The data sheet lists as an inorganic thickener, but then it gets very specific about the base fluid. And I have to admit, this jumped off the page at me. It says it is formulated using food-grade polyester base fluids.
Oh, yeah.
Wait, food-grade polyester? Are we lubricating an industrial pipeline valve? Or are we picking a highly synthetic cake? Like, why use a polyester base instead of a standard vegetable-based fluid or just a heavy-duty petroleum oil?
It sounds totally counterintuitive, I know. When we hear polyester, we picture cheap 1970s clothing, right?
Exactly.
Not heavy industrial machinery. And calling it food grade just makes it sound, well, delicate.
No.
But if we look at the underlying organic chemistry, polyesters are just a highly versatile category of polymers. The engineers didn't choose this synthetic base fluid randomly. It is a highly calculated defensive strategy against a very specific enemy.
The enemy being the actual oil and gas flowing through the pipe.
Precisely. Propane, butane, crude oil. These substances are largely aliphatic hydrocarbons. And in chemistry, there is a golden rule: like dissolves like.
Oh, okay.
So if you use a standard petroleum-based grease to seal a pipe full of liquid petroleum, the crude oil flowing through the pipe will simply dissolve your sealant. It will wash the grease right out of the valve, and you'll have a catastrophic leak in a matter of hours.
That makes total sense.
Yeah, and even traditional vegetable-based fluids can break down or react under those really harsh conditions.
So by using a synthetic polyester base, the sealant fundamentally ignores the aliphatic hydrocarbons. It's essentially like an invisible force field. The crude oil washes over it, but because the chemical structures are so different, the oil just can't dissolve the sealant.
Yeah, it sits directly in a stream of high-pressure gas or oil without breaking a sweat. It just chemically ignores the harsh environment entirely.
Okay, here's where it gets really interesting. Because a sealant doesn't just block fluids, right? It also has to lubricate the moving metal parts of the valve so the massive heavy machinery doesn't get stuck.
Absolutely.
And the data sheet heavily highlights a specific additive, molybdenum disulfide, or MoS2. Can you explain the actual mechanism of MoS2? Like, what is it actually doing inside the valve?
Yeah, so molybdenum disulfide is an incredible solid lubricant. If you were to look at it under an electron microscope, its molecular structure actually resembles a deck of playing cards.
The deck of cards.
Yeah. So when two massive heavy metal surfaces press together and try to move past each other, those microscopic cards easily slide and slip off one another. This drastically lowers the physical friction between the steel parts. The datasheet explicitly notes that this lowers the torque necessary for smooth valve operation.
Meaning the giant wheel an operator has to manually spin to open the valve is physically easier to turn, which prevents the mechanism from jamming.
Exactly.
But the document suggests it goes way beyond just making things slippery. It states that MoS2 enhances sealing and lubrication by burnishing into scratches. It actively renews the internal metal surfaces.
Yes, that word burnishing is the key to the whole operation.
I was reading that and picturing like microscopic spackle. It's basically an anti-aging cream for industrial metal.
That's a great visual.
It's not just sitting passively on the surface like normal grease. When the steel parts of the valve rub together under thousands of pounds of pressure, that immense physical force literally crushes the MoS2 particles into any microscopic pits, gouges, or scratches in the metal. It actively patches the battle damage in real time as the machinery operates.
That microscopic spackle analogy is spot on, and the stakes for that process are incredibly high because it protects against a catastrophic mechanical failure engineers call scoring and galling.
Galling sounds terrifying. That's when metal destroys itself, right?
It is a total nightmare scenario for an engineer. Galling happens when two bare metal surfaces under extreme pressure basically friction weld themselves together for a fraction of a second.
Oh, wow.
Yeah. And as the valve continues to force its way open, it violently tears those microscopic welds apart, literally ripping chunks of steel out of the valve wall. It destroys the machinery from the inside out.
Yeah.
But by forcing that deck of cards structure into the scratches, the MOS2 forms a sacrificial barrier. It ensures that bare steel never actually touches bare steel.
Okay, so we have a polyester base ignoring the oil and a MOS2 actively healing the metal. But physical wear and tear is only half the battle here.
Right.
Because if you look at the inside of an industrial pipeline, it is basically an active chemical warfare zone. The datasheet specifically notes that the formulation contains hydrogen sulfide or H2S inhibitors. It says this provides a longer product life in sour gas service.
Yeah, and if we connect this to the broader challenges of the energy sector, you start to understand just how destructive sour gas really is.
What makes it sour?
Well, when raw natural gas comes out of the earth, it often contains high concentrations of hydrogen sulfide. That's the sour part. And H2S isn't just incredibly toxic if inhaled by a human. I mean, but it is also notoriously aggressive toward metal.
Really?
Oh, yeah. It causes a phenomenon known as sulfide stress cracking. It literally attacks the molecular structure of the steel and makes it brittle over time.
So the environment isn't just under pressure. It is actively trying to eat the valve from the inside out.
Exactly. And that means the sealant has to be much more than just a physical plug. It has to act as an active chemical shield. The H2S inhibitors engineered into the paste neutralize that corrosive attack right at the boundary layer, protecting the vulnerable metal underneath.
And it's fighting off water at the exact same time. The sheet lists a water washout rating of less than 2%, and its water solubility is listed simply as none. 0.
Right, it just completely ignores water.
Which is crazy. And I noticed a physical metric earlier that makes so much sense now in this context. The specific gravity is listed at 1.11, meaning it is roughly 11% denser than water. So if water floods the system, the sealant doesn't just float away, right? Its density anchors it into the microscopic gaps of the valve.
It stays exactly where it was engineered to be. It's brilliant.
And looking at the stability test, it just stubbornly refuses to degrade.
Yeah.
There's an evaporation loss metric, less than 0.5 over 24 hours at 150 degrees Celsius. It also boasts an oxidation stability rating of less than a 5 psi pressure drop over a full 168 hours.
That's a whole week.
Right. Think about what that actually means. It is sitting in this hellish, hot, chemically toxic environment under crushing pressure, and it just, well, holds its ground. It doesn't evaporate, it doesn't dissolve, and it doesn't break down.
Which brings us to its physical profile. We are talking about a material the datasheet describes as semi-plastic.
Right.
How do you actually measure the toughness of something that isn't quite a liquid, but isn't quite a solid either?
Well, the physical stats paint a picture of a really bizarre material that comes in two different forms. Bulk, which is the pumpable paste we talked about earlier, and stick, which is essentially a dense cylinder you load into a specialized injection tool. And to measure how firm these forms are, the industry uses a metric called cone penetration. The sheet lists it at 225 to 245 for the bulk paste, and a much firmer 70 to 100 for the stick. Walk us through the mechanics of a cone penetration test. Why do we care about this number?
Okay, so a cone penetration test is a standardized way to measure the exact stiffness of a grease or sealant. You take a standardized, weighted metal cone, place its point perfectly on the surface of the material, and drop it.
Just let it fall.
Yeah, you just let it sink into the paste for a very specific amount of time, usually 5 seconds. The depth that the cone penetrates, measured in tenths of a millimeter, tells you how firm the material is. A higher number means the cone sank deeper, so the material is softer.
So the bulk paste has a higher number, 225 to 245, because it needs to be soft enough to be forced through a pump.
Exactly.
But the stick form needs to hold its cylindrical shape until the very last second, so it has a much lower, firmer score of 70 to 100.
Precisely. It allows engineers to choose the exact physical consistency they need for their specific mechanical application.
But the metric that truly blew my mind is something called the 4-ball weld point. The datasheet lists it at an astonishing 620 to 800 kilograms. I had to look up how this test works, and it is visceral.
Oh, it's intense.
You basically take 3 steel balls, lock them together in a triangle, and put a fourth steel ball directly on top of them. You coat the entire cluster in this sealant, spin that top ball at incredibly high speeds, and then you start applying hundreds of kilograms of crushing downward force.
And you just keep going.
Right, you keep adding weight until the physical friction gets so intense that the steel balls literally weld themselves together into a single chunk of metal.
It is an incredibly brutal test designed to measure extreme pressure resistance, scoring between 620 and 800 kilograms of downward force before the metal fails and welds together is exceptionally high.
Which tells us that the MOS2, those microscopic DEXA cards we talked about earlier, are doing the heavy lifting here.
Absolutely.
The MOS2 is taking the punishment so the steel balls don't have to. It keeps the metal separated even under crushing industrial loads.
The solid lubricants are absorbing the friction. And if you look at another critical metric, the dropping point, the datasheet simply lists it as none.
None, meaning no matter how incredibly hot the environment gets, the paste never actually melts into a pure liquid that drips away and abandons its post.
Right.
It might chemically degrade if oxygen is present, like we said, but it will not liquefy. It's a spectacularly tough profile.
Yeah.
Which leads me to the most important question for any engineer: is this stuff virtually indestructible? Like, where does it actually fail? Because every single superhero has a kryptonite.
They do. And to utilize a tool correctly, you have to fully understand its absolute limits. And JetLube is very transparent about the kryptonite for this product. The datasheet explicitly warns that EZY-TURN number 4 is not recommended for steam service or highly alkaline service.
Why steam? We already established it handles 400 degrees Fahrenheit with ease, so it's clearly not the heat causing the problem.
No, it's not the heat. It's the violent physical mechanics of steam. Steam isn't just hot water, you know?
Yeah.
It involves high heat, water vapor, and extreme velocity. When steam rushes through a valve, it can physically scour and blast the semi-plastic material right out of the microscopic gaps in a way that slow-moving liquid water or heavy crude oil simply cannot.
Okay, that makes sense. And what about the warning against highly alkaline environments? The sheet mentions the sealant has its own pH range of 2 to 9, so it naturally sits somewhere between slightly acidic and slightly alkaline.
The issue there is a chemical attack. If you expose the sealant to extreme alkaline caustics, basically liquids with a very high pH, those chemicals will actively attack and break down the food-grade polyester-based fluid we discussed earlier.
Oh, so the synthetic shield would dissolve.
Exactly. The shield drops. But the biggest warning, the absolute red alert kryptonite, is printed clearly at the bottom of the data sheet. It must never, under any circumstances, be used with oxygen or strong oxidizers like hydrogen peroxide or sulfuric acid.
Tying right back to the 500-degree rule we discussed at the very beginning, oxygen is the ultimate enemy here. If you were to mistakenly use this sealant in an oxygen-rich pipeline, you aren't just risking a minor leak.
No, you are risking a catastrophic event. Strong oxidizers will violently tear those synthetic molecules apart. It could trigger a rapid chemical reaction or even a severe fire.
Wow.
Yeah, the compound is virtually indestructible against oil, natural gas, water, and heat. But a direct blast of pure oxygen or acid will utterly defeat it.
Which brings up a really practical logistical issue. Imagine you are the maintenance engineer who actually has to clean this valve out during a shutdown. If this semi-plastic, metal-healing, hydrocarbon-ignoring goop is so incredibly stubborn, how do you actually remove it?
It's a real problem.
Right. You obviously can't just wipe it down with a shop rag and some soapy water. The water washout is basically zero.
Yeah, standard mechanical cleaning methods would be completely useless. You would just smear the paste around. Because the material is so chemically stubborn, you have to use targeted chemistry as a weapon against it.
And the manufacturer actually provides the antidote. The datasheet recommends using a companion product called EZY-Open or other safe oxygenated solvents. EZY-Open is a cleaner specifically formulated to defeat this exact sealant.
And notice the specific terminology there, oxygenated solvents. Since the engineers know that oxygen and strong oxidizers are the product's ultimate weakness, the custom cleaner leverages that exact chemical vulnerability.
That's so clever.
It is. The oxygenated solvent aggressively breaks down the polyester bonds, dissolving the paste entirely so it can be safely flushed out of the valve.
So what does this all mean? We've spent this deep dive exploring a single, highly technical datasheet, and in doing so, we've mapped out the chaotic life of a truly bizarre, highly engineered substance.
Yeah, it's quite a journey.
We're talking about a gray-to-black, semi-plastic compound that goes to war against sour gas. It survives freezing Antarctic blizzards at -40 degrees and survives 500-degree infernos by literally holding its breath inside an oxygen-starved valve. It uses microscopic layers of MoS2 to actively heal and protect metal surfaces from friction welding themselves together, and it relies on a food-grade polyester shield to stand stubbornly against rivers of aliphatic hydrocarbons.
It really is a marvel of specialization. I mean, it is engineered to do one highly specific job in some of the most hostile industrial environments on Earth, and it executes that job perfectly. But if we pull back and look at the broader implications of this document, there is a final, fascinating observation we can draw from the environmental ratings.
Oh, what stands out too?
Take a close look at the environmental profile of the sealant itself and the chemical cleaner used to remove it. Despite being rigorously engineered to battle the harshest, most chemically aggressive, highly pressurized, toxic environments in heavy industry, EZY-TURN number 4 is explicitly rated as non-hazardous and biodegradable.
Wait, really?
Yes. Furthermore, the cleaner, EZY-OPEN, is rated as non-toxic, non-flammable, and biodegradable as well.
Wow. Amid all the talk of toxic sour gas and 800-kilogram weld tests, I completely glossed over the environmental rating.
It is a profound paradox to leave you with. To conquer the absolute most toxic, high-pressure industrial environments, human engineers didn't rely on harsher, more dangerous chemicals. They didn't build a toxic, indestructible monster to fight a toxic environment. Instead, they designed a highly technical, elegant solution that nature itself can safely break down.
That is an incredible paradigm shift.
It makes you wonder, does the true future of extreme industrial engineering lie not in building monolithic things that are utterly indestructible, but in building intelligent things that are perfectly harmonious with the natural world?
The hidden armor holding our industrial world together isn't just tough. It's designed to eventually fade away without a trace. A biodegradable shield standing against extreme chaos. Something to think about the next time you drive past a sprawling refinery or see a pipeline vanishing over the horizon, and you wonder what's really holding it all together.